happens only, I will receive. If it happens only, he receives, and it can be controlled using the coding. And that's the amazing part of what it is. But anyway, this is another pay to public key, P2PK, pay to public key. The 2 is TO is replaced by number 2. So P is always pay to. So the remaining is PK, PKS, PK hash, PK witness. So all those things come in, right? It's a script pattern that logs an output to a public key. It is a simpler version of more commonly used P2 PKH, right? So you can look at the script. So it, there's a signature, it goes, and then you have this and check the signature where it is right. So it's a very simple protocol that you can look at. So signature is first pushed, then you check it, and then you check it to the run and place 1. So it's a very simple script here for pay to public key, right? And then you have public key hash. So here is hash is taken extra. So that's what it is. P2PKH is the default script used by wallets, which are commonly used. Any wallet that you look at, Bitcoin wallets like exchanges that you, and they have their own wallets, and you can use those wallets. So P2PKH, the hash part is also used. So if you look at it looks something like this. The script signature first goes in, then you have a signature on top. So duplicate it, insert it, then you take the hash of it, and then again the signature comes. The signature is compared, and both of them are correct. Then you check whether the signature is on top. Yes, then you place a value 1. Right. So this is how the thing. So I just you observe it, you will understand. Yeah, hopefully you understood. So I don't know whether I'll be able to share the animated version, but let me see. At least I will send the animations to you separately, and the remaining part of the slides. And of course, I've taken it from somewhere. It's mentioned here, right? That part you can look at that. You go there and get the what do you say? These animations you can look at, right? So it's mentioned somewhere behind me. Learn me a bitcoin.com, right? So that's where the slides are, so you can go and get that, right? So hopefully you're able to understand what we are doing, and this is all going on, so it's madness. So there are so many things which are being done on blockchain, and we are only worried about money. So I think we should move from that, right? Here is slightly interesting. Some of the work we are doing, multi-signature. We have submitted 2 papers on this. Hopefully, maybe next time when I take a talk on blockchain, I will share the paper with you, because it is currently under review. So it is called multi-signature script. Multi-signature script there are so many public keys, there are n public keys in the script, and at least m of them must be provided to unlock the funds. So it is not one signature being correct, but it is n of m signatures being correct. There are m signatures, n of them are going to be provided, and because of that, it's called an M of n scheme, right? So M of n public keys must be verified, right? So n is the total number of keys, and m is the threshold of signatures required for validation. That means out of n, some m must be available. The threshold means some number again. So if there are 10 keys, so 8 can be a threshold, 6 can be a threshold. So 6 of 10 or 8 of 10. Okay, this is the model that we are looking at. So the general form of locking script setting M of n, multi-signature condition is m public key 2. So there are n public keys, and there's a number m, and you have to check the multi-signature. So that's how it looks like. So there's an example, and some of the times maybe you are looking at these scripts, they are actually picked up from the live blockchain, the Bitcoin blockchain. These are examples. I should have actually put the what do you say, the block also. So then you can go and actually check this kind of transaction exists. So this is the kind of transaction which is there to public key, and so there's so many partner, and then finally you have the check multi-sig. So this is the kind of script that will get created. So here this 5, and then this is a multi-signature check, right? So that's the kind of thing that happens. So they are longer locking scripts, and hence P2SH is a simpler script. It solves the issues of multi-signature script. So what you do is the complex locking script is replaced with its digital friend, which is a simple cryptographic hash. So a smaller value set. So when the transaction attempting to spend the UTXO is presented, it must contain the script that matches the hash in addition to the unlocking script. So instead of sending that whole UTXO, the whole hash also onto the transaction, this whole part starting from D7 onwards till this 7D, that whole 5-6 lines, I think 1, 2, 3, 4, 5, 6 lines, that whole content is adding to the size of the that has to give a hash of that value, which will be smaller in size, and that is sent. But then this expanded version has to be given. So it will be stored in another database somewhere, and when the reference comes, you will provide that reference, and then it goes. So it doesn't add to the blockchain's size. The transaction size is not added. So P2SH means pay to script matching this hash. P2SH means pay to a script which is matching this hash. A script that will be present later when this output is being spent. So that script will come at a later time. The locking script is replaced by a hash is referred to as the redeem script because it is presented to the system at the redeem time rather than as a locking script. The script is not available. When you are unlocking the script, then the script is presented. So that is how it looks like. So this is how you can see the example. So that script sig is available. That whole thing goes into it. Okay, and now a copy is maintained. So you pop it, and then you get the hash 160 of it. Then you check whether both of them are equal. If both of them are equal, you place 1 on top of it. And if on the top of the stack, if it is 1, you can do that, right? And now you can check the output is like this. So you take out, okay, you check at every levels, you check, and then you get the value 1, right? This is how a P2SH script runs it. Okay, maybe you can look at it again. Now your copy is maintained. Then you take up and get a hash 160 of it. Then you take the next value, which is already there. Both of them are equal. You place 1 on top of it, right? So once that is done, then this copy is taken and the copy is evaluated now, right? So 2 and 3 signatures are coming in. You are checking, placed. So this is how the P2SH script works, right? So complex scripts represented by a shorter fingerprint. That is the advantage of P2SH. It shifts from obstructing the script to the recipient, not the sender. The sender doesn't have to put all the script in transaction. The so it doesn't go into UTXO. Script doesn't go into UTXO. Okay. So, but it shifts the burden in the data storage for a longer script from the present time to a future time when it is spent. So when the transaction is made, we don't have to worry about the entire script, because when somebody wants to spend that, at that time the transaction output is to be executed, right? So it shifts the transaction fee cost of a long script from the sender to the recipient. So when he wants to spend it, then he has to pay more for that, right? So that's how it happens. There is a hash lock script also, which is there. So transaction is locked until a specified data is revealed. So a hash value should be revealed, right? It can be used in various applications, which I discussed. Atomic swap, I just discussed with you. Both parties cannot swap their funds unless a secret used to lock the transaction is exchanged between them. So once that is there, so you can do that. So there is a operation hash 160, then a hash value is there, and you check whether it is equivalent to equal verify or the duplicate value of that 160 hash, and then you get the hash of the public key, and finally verify whether there is a signature which is equivalent to what is being generated. Then it is 1. If it is not equal, then it is not 1. So in the input script, the sender has to reveal the secret such that its hash results in the hash mentioned in the output log. So you see the size of the script, you send the signature, you send the public key, and script till give me 1 minute. Sorry for the inconvenience. Yeah. So here you have the output script, the script to log bitcoins until specified expiry time. So after that, the funds can be spent by signing the output with the specified public key in the script. So till the time this is locked. And similar thing where a hash is revealed, then you can spend it. Here you can set it particular time, and before that, till that, if the time expires, then you can go ahead. The transaction output is locked until a specific time or a specific block height is reached. You say some 100 blocks should be created, or so much time. You also know every 10 minutes one block is created in Bitcoin. So in 1 hour there are 6 blocks which are created. So if you want 100 blocks, some 16 hours have to be spent. So you can set the time like that, that after so and so time you can. It can be used in applications when you are wanting to invest in Bitcoins until a point of time. You think that you guess that maybe after 10 days the Bitcoin is going to go up, and at that time you want to spend the Bitcoin. So you can time it now itself, and you can continue with that. So that's an output script. The script to lock Bitcoins until specified expiry time. So after that, the funds can be spent by signing the output with the specified public key. So it's called a time lock script. So spent only after waiting for the expiry time. So you have the signature and the public key in the input script. So that's all. And when it goes and it checks the time, and then you can get it, right? And the last scripting conversation that we can look at is the protocol that we can look at is pay to taproot. So this is a major Bitcoin upgrade rolled out in August 2021. And of course, I said last year, but it's 2021 where it was. And then finally, it takes time for them to understand. So the Schnorr digital signatures were introduced, and P2 pay to taproot transactions were also introduced. So pay to taproot allows what is called a script path or a key path spending of a transaction output. There are two ways. You can either do it to a script path or a key path. So if a P2TR output is unlocked using key spending path, the possibility of spending through a script path is not even revealed. So there are two options. But if it is spent, if it can be unlocked using a key path, people will not know whether there is a script path or not, right? If a particular script path is used to unlock the output, the other scripts are not revealed, right? So the key spending path is not revealed. So it saves space and transaction fee on the unused conditions to be specified by the spending party in the transaction, right? So when you want to spend it only, then only the script is required. Till that time, we don't have to do it. So, and it also increases the privacy between contract between these things. So features are indistinguishable locking and unlocking for spending Bitcoins using script or key path, right? So there is an alternative signature scheme. Similarly to that is called what is called a Schnorr signatures. They allow aggregation of public keys for multi-signature transaction, making it appear as a single party signature on chain. So the Schnorr signatures, it takes multi-signature, which we discussed briefly. So the multi M of n signatures kind of thing, and then it takes a multi-signature public keys, taking all of them, but then it appears like a single key only. So that is the greatness of Schnorr signature. So you can, if you're interested, definitely Schnorr signature papers are there. Many papers are there on Schnorr signatures. These days we find some papers also on Taproot. And till couple of years, last 21, 22, 23, where we were researching on Taproot, we have never found not many technical research papers published, but mostly available as what you call as a white papers or as blogs, or somebody writes a GitHub repository, creates and leaves it. So we also have created a GitHub repository called libmultisig, right? If you want to explore all the transactions that I've mentioned, they are available as libmultisig. You can look up GitHub, and then you can download that whole library and run all those transactions and see. And you can also trace those transactions on Bitcoin. So whenever you see a blockchain, these Bitcoin explorers you can use and see each block, and each block you can see some transactions. You can identify which kind of transactions are there, and then you can see whether it's a P2SH or P2WSH or P2SK, or all these kind of combinations. And it's a good learning. So that library is there, and how to use them you can check out, right? So I think somewhere down the line we will discuss that, right? Specifying transaction spending paths in the form of a data structure called Merkleized abstract syntax tree called MAST. So you can have a batch verification of multiple signature. It also saves time on individual verification because everything is time bound. So that is what it is. When you look at a pay to transaction, a pay to taproot transaction, this is how it looks like. So the output locking script, witness version 1, and then there's a 32 bytes taproot output key. So the taproot output output key will be Q is equal to P plus hash of P and the multi-signature M and find out by this G. So the P is taproot's internal key corresponding to key path spending. It can be the public key whose signature is required for spending the output, right? In case of a multi-signature transaction, it is an aggregate public key. What is M? M is the root of the Merkle tree whose leaves represent the possible ways to unlock the output, and G is generator point on the of the elliptic curve. So that is something that you can look at, right? So that's what can be thought of, right? So 1 minute. So we have this formula taproot output Q is based on P plus hash of P. Or you can take the what is that OR of that, and then you can get M and then multiplied by G, which is generator point on the elliptic curve. So these things are to be identified. So how do we do that? So if you look at a script key, the script key will be all possible script paths for unlocking an output are arranged in a Merkle tree, right? So scripts are arranged as Merkle tree leaves, right? So as you see, tap leaf, these are the tap leaves. These are the scripts which are arranged as leaf nodes. So they are all the tap scripts that are available, right? And then you merge all of these. So AB, so based on these, you create AB. Based on these two, you create CD. AB and CD merge to become ABCD, and then you finally get the script root, right? That's there. Okay. So the key spending, as you look at the unlocking script, it will be a signature corresponding to the taproot followed by P. Okay. So script path spending unlocking script consists of the following: the taproot's internal key will be there, the script which is used to spend the output, and the inputs for spending execution of the script. So the Merkle path from the unlocking script to the Merkle tree root, this confirms the presence of the script in the tree. So you can find out the Merkle path also, and then you can check it. So these two things have to be done. So this is what we did as a contribution from our side, libmultisig. So we created a multi-signature library on Bitcoin, right? So this it's a console-based application to construct multi-signature contracts. So if you want to create scripts and you create locking and unlocking scripts, you can put this, and then it includes various configurations of key and script paths in P2TR transactions, all those things that we have discussed. And it examined the aspects such as locking and unlocking, the transaction size, type of address, number of transaction rounds required between the involved parties. All these things are there. So output key path multi-signature P2TR, the output is logged in key path as public key of a recipient. So you have music, which is 1 or 2 or 3. So the multiple public keys are aggregated as a single key. So it's called a one key path multi-sig P2 taproot. Just P2 taproot is a one version of the protocol that is used. And in that, again, you have one key path multi-sig transaction. M of n, tap script multi-sig transaction. So there's a key path and there's a script path. So you can see the script path is starting from the right-hand side. The key path is starting from the left-hand side. The multiple public keys aggregated as a single key. That is the key path. And if you look at a script path, it is a tap loop M of n script. 2 of 3 is M of n script, which is there. It's the tap script and a predefined threshold of participants based on that. And then again, you can get a taproot output key. So these both add on to become what is, and you can use either one of them. You can use a key path aggregation, or you can use a script path aggregation. So that's something which I can look at. And M of M transactions. So when you use multiple public keys aggregated in a single key is a key path. That is there, the first one. The second one is M of M transcripts. A predefined threshold of participants are there. 2 of 2 transcripts are there. 2 of 2 transcripts are there. Multiple transcripts are there. And then you merge all of them, and then they create what is called a taproot output key. So the M of M transactions and M of N transactions, there's a slight variation that you can look at. And multiple M of M transactions. Now, variety of such things go on, and it becomes very difficult to manage. So there's a key path, multiple public keys aggregated as a single key, and script paths, tap leaf, M of M music transcript. Predefined threshold of participants as aggregated public key is also mentioned here, so we can use this kind of mechanism. Only script if you want to use, so no key path is there. Everyone agrees way is not possible. So what you do, you have tap leaves, possible combinations of multi-sigs and tap scripts, and you can do that. And then you have top branches, and the top branches are merged finally to become what is called a Merkle root, and then you get a output key. So there is only a script path here. There is no key path. Key path is there on the left hand side. Now you have only this part, which are called only script path multisig. When you do an assessment of how it happens, right? So pay to multi-signature, pay to script hash, pay to witness script hash, pay to script hash, and pay to witness hash combination. So you can see 2 of 3 multi-sig, so different kinds of output. So you see output script, the number of this thing. So 105, 145, the script size, and it increases. So P2SH input script increases. P2WSH is there is 34, but there is no script sig here. But when you look at a combination between these two, so there are this kind of things as the totals increase, right? So this is how here there is no witness, here there is no six script, but here there is everything, and you can do that. Two types hash clocks. Basically, a hash must be there, which will be an hash, and you get the correct value, so you can unlock it. Then you have a time which has to spend the time, and you can't claim them before that particular time is spent. So that is how you can do that, right? So when you want to do in a blockchain, how you want to use it. So there is one individual A which places a lock on the funds, knowing the secret phase, and sets an expiry of 6 blocks. It's a time that is spent. So this B gets a BTC amount. He enters the secret phase, unlocks the fund, and claims within 6 blocks. So before 6 blocks, he has to do that. So that's a success scenario. So he sets an expiry of 6 blocks, but he does not claim it. So what should happen? The amount should be sent back to him. That's a refund scenario. And then in an atomic swap, we can use the scripting and use in atomic swap. Atomic swap, what is happening? Atomic swap, I am trying to make a transaction from Ethereum to Bitcoin. So I have one person has Bitcoin, the other person has Ethereum. They are exchanging. This person is giving Ethereum there, and that person is giving Bitcoin here. So Alice is A is on Ethereum chain, B is on Bitcoin chain. So there is E on escrow. E is there on both chains to lock the fund. So Alice is transferring E Ethereums to Bob, and B is transferring B Bitcoins to Alice. So the result is exchange. So many ethers equivalent to so many Bitcoins are exchanged. No problem. Otherwise, both will get back their money. Rollback happens. So that is how it happens. So you have a lot of cross-chain transactions also. So they are done through non-atomic transfer, or they're doing through centralized exchanges, decentralized exchanges, or what is called an escrow service. Escrow service is a trusted third party. I will put money, you will put money, we both will get back our exchange. It's called an escrow service, right? So the disadvantages are, for all these transactions, they charge money. So you lose a lot of transaction cost. You have additional points of failure. Somewhere the transaction fails. Now, whom do you ask on a blockchain environment? Very difficult, right? It requires trust in the mediating third parties as well. So that's a cross-chain transactions that we look at. The third party custodial escrow service, if you look at it, so there is an E, which is an escrow service. The funds are sent across chains after deducting a fee. So when I want Bitcoin amount to be sent to escrow, I have to pay some fee. The Ethereum amount I have to spend some transaction fee. Then when the amounts are exchanged, again I have transaction fee. So finally, escrow is the benefiter, but A and B are losers just because they are doing the transaction. So the other aspect is an atomic swap that we look at, right? So the atomic swap, there is a dual escrow mechanism. First is on Bitcoin chain, second is on Ethereum chain. So there is no need to have an escrow service. They can be done by the users themselves. So what you do, Alice owns Ether, Bob owns Bitcoin. Now, atomic swap protocol succeed. Alice gets Bitcoins, Bob gets Ethereum. Protocol fails, Alice keeps the Ethereum, Bob keeps the Bitcoin. So no problem, right? Transactions in case of protocol success, BTS is locked on the Bitcoin blockchain, ETH is locked on the Ethereum blockchain, unlocks Bitcoin for Alice, and unlocks information for Bob to claim funds. Unlocks Ethereum for Bob on Ethereum blockchain. One of them will have to be successful, but what happens is, the moment the fourth step is unsuccessful, the third step is reversed. So that is how the scripts are planned, right? So first Bitcoins are unlocked for Alice, and she sends the unlock information to Bob. Bob will claim his funds. If Bob is not able to get back the money, then obviously Alice will have to refund. The protocol will ensure that. So that is how an atomic swap can happen. While this atomic swap is also happening, somebody has given this protocol. There is privacy concerns in that. Amazing, right? So just imagine how much people are thinking and how much people are trying to compromise. Where I will get more money, where I can dump a transaction, where I can go free, because nobody can catch you after you unless until you are two good friends and you know your public address, public address and physical locations, right? If you are friends with some virtual friend, the virtual friend can just cut off from the virtual world and he is not available, right? So just see this high-level process, what happens. Alice and Bob exchange some parameters. The exchange rates are set between the Bitcoin to Ethereum. They can set it among themselves. Addresses they want to receive funds on, they exchange that. Bob generates a secret key and shares a hash of the secret with Alice. Expiry time is set for both Alice and Bob. So there is a lock. Bob locks Bitcoin on Bitcoin Ethereum. Alice locks Ethereum on Ethereum blockchain. So ledger redeem. So Alice redeems the Bitcoin, revealing a secret. Bob redeems the Ethereum using the said secret. So both get their money. Otherwise, it's a refund. Bitcoin. Bob is refunded on the Bitcoin and Alice is refunded on Ethereum. So that's how simple is the atomic swap running. So these are again the scripts that are there. P2WSH scripts are used. Transaction by Alice on Bob, and so there are some conditions. So there is hash of the secret key, the hash of the next value that is placed, Bob's public key is placed, and you have the Alice public key also, and then you are successful in that, right? So that's how the first step one. Step two, transaction two by Bob on Ethereum. So he gives that value and it checks whether till that time is specified. So this is how the EVM Ethereum code looks like. So the redeem script is given by Alice on Ethereum. So there's a contract address, there's a data secret. So what do? You send the contract address and then you destroy the smart contract on Alice side. It is over. So the redeem script by Bob to Bitcoin. So you get the Bitcoin signature and public key. There's a secret which is given, and then you can try to do that. So when the analysis is being done on both transactions, if somebody is following these transactions just like that, just somebody is analyzing these, how these transactions are being made, and suddenly he finds that these two people are making these transactions, and he's trying to guess that these transactions on Ethereum and these transactions on Bitcoin are related because the amounts are relevant. So you can try to make a comparison, and then you can try to arrive at that. And because both chains are public, transactions can be analyzed, and linking of addresses on both blockchains are possible. So when you link those addresses, then you get what is called a privacy issue. So obviously you move to and we are actually giving a protocol here. We have given top tap to escrow. One paper is already under review. So two papers we are doing. One on Taproot and one on the tap to escrow protocol, where we are doing atomic swaps and trying to share or make the conditional transactions possible. And we found out privacy issues in that. We're trying to overcome those privacy issues by doing that. So these are kind of atomic swap transactions on both blockchains. They can lead to anonymity issues. So we can understand this. So another blockchain which comes as an example here is the privacy preserving blockchain called Monero. So Monero has this cryptocurrency which enhances privacy using stealth signatures or ring signatures or confidential transactions, right? So the first thing that Monero has is what's called stealth transactions. Stealth transactions is where Alice and Bob are sending to Charlie's transactions. So at least a linkability is established that this is Charlie and Alice and Bob are linked to Charlie. Some kind of combination you can try to get. But when you unlink those transactions, which is done in Monero, it gives two different addresses for Charlie. Charlie doesn't have the same address. Alice shares to some Charlie's address. Bob shares to some Charlie's address. Charlie is the same individual, but he has two different addresses, so the unlinkability is maintained. So the address on the blockchain is going to be different than the actual blockchain. So two different addresses point to the same address of Charlie. So that's what we mean to say here. So then unlinkability is maintained. The second thing is basically the output is derived from one Monero address of the user. Only the owner of that Monero address knows the output is for him using view keys. Virtual keys are maintained, and virtual keys are maintained are created, and the virtual keys are maintained somewhere so that you can go to view keys and know that. Okay. Nobody can tell that these two keys are separate except the person who has both the keys. Only he knows that I have, oh, both these keys are mine, but nobody else can guess. So that's a kind of a privacy security that is coming in. One is traceability. Traceability is where you can see that transaction A, transaction B, transaction C goes to some addresses. These some addresses go to Charlie's addresses. So they know the relationship between Charlie, A, B, C. So transaction ABC is coming from 3 different sources. They're coming to some addresses. From those addresses coming to Charlie. So it's able to go back to that right now. So what happens is these transaction A, transaction B, transaction C comes with some intention, and they say that it's coming to the same address. But what happens here? Here the addresses are different. So the one single address has multiple addresses. Every transaction is coming to one of those addresses. So we are not able to link all these addresses, which are all these transactions are coming from 5 sources or 3 sources coming to the same transaction. They are not linked. So the 3 transactions are 3 different transactions. The 3 different transactions are sending money to Charlie as 3 different transactions. So the entire transaction process is untraceable, right? So that is what it gives, and it uses what is called ring signatures. Now, ring signature is an important concept you can look at. So if you understand who is there, so the ring signature, what it does is at least one real participant and others are mix-ins. Mix-in means they are not the actual participant, right? So that's something that you can look at. Mix-ins are output for some previous transactions. So what they do, these two users had many other transactions. So they take the previously used transactions and then they put it inside as unspent transactions, and then they are using that just to add transactions. Only one transaction is correct, but you send 5-6 transactions, and then 4 of them are not correct, or one of them is correct. So we are confusing the people who are observing the communication between two users, right? There's a ring signature is used to create. So for a verifier, no way to tell who is the real participant. So there are 4 people who have locked their inputs with the key, and then the message is transmitted on the other side. 3 public keys are used, and then you try to find some blocks on the blockchain with the same amount X as output A that you want to spend, and what you can do is you can bring it to where you want to spend. So that is something that you can try to understand, right? So find some outputs in the blockchain with the same amount X as the output A you want to spend. Let us say you want, and then you can create mix-ins. All mix-ins will be of the same value. You can use 4 to 25 mix-ins in a transaction, 4 to 25 mix-ins. So you can send 4 transactions or 25 transactions of the same modified version of the transaction. And one of the transaction is correct. All the other transactions are already unspent transactions. So you can sign this using what is called a ring signature, right? So when you have a ring signature here, so you have, it's easy to verify that at least one user from inputs have signed this ring transaction. Not easy to find which user has signed the transaction, and you can do that. So there's Alice, Bob, and Carol for verifying, and you can do that. So how does the mix-in work? This is an example. You want to send X bitcoins. So you pick up different transactions with X bitcoins as output. So all the transactions will have X bitcoin. It's something like you are defeating, like let us say the Prime Minister's car is going. The car, when it goes, it doesn't go as a single car. If it's a single car, people can target it. So there are 5-6 cars of the same type when it is traveling on the road. So you don't know which is the car that the Prime Minister is traveling. So that is something that you can look at. So there's a new transaction, the input, and there's an output reference A, O, B, C. So many are there, but real input is O, A, B, C are there. And Bob's output address is amount is X. So there's an address. So what you try to do is output will always, all of them are going to the output Bob's address. All of them are sending the amount X, but only one of them is correct. So that's what is the real using the ring signature, this possibility is done, right? So and then there is also some confidential transactions which are made. So the transaction amounts are visible as blockchain data. It's public. So people also know how much money you are transacting, right? So what you can try to do is you want to hide the transaction amounts to provide financial privacy. So it's one such cryptocurrency to use bulletproof technology. Please read through. There are a lot of papers on bulletproof once you want to research on that, right? Actually, bulletproofs are called short, non-interactive zero knowledge proofs, NIZKP. Zero knowledge proofs you must have studied, you must have heard somewhere. Bulletproofs are non-interactive zero knowledge proofs. So these are used basically to create confidential transactions. They provide that the encrypted input and output for a transactions are in given range, and without revealing any other information about the numbers, you can get the transaction. So there is something which is called a Peterson commitment. Peterson commitment, and you use a simple formula where commit of x or and is maintained by g power x and h power r. So x and r values are there, and you can try to create these values. So actually amounts are not displayed, but the cryptographic values are displayed. So you can, based on the existing keys and existing values, you can directly calculate the actual amount being transferred here. So that's something that you can look at, right? So they use what is called Peterson commitment, and the transaction amounts are hidden. The transaction graph is still public. Everybody can see all the transactions, but they don't know how much transaction it is there. There is a cryptographic code there. So it allows public verifiability of transaction validity by other users and miners, but still it allows the confidentiality to be maintained using what is called Peterson commitment. So this is the example. C is equal to g power x h power r. X is the value to be obfuscated. So you want to hide the x value. R is a random number. G and h are distinct generators on the elliptic curve, and based on that you get the value. So it is binding such the prover cannot later come to another Rx that gets to C, and it is hiding such that it is difficult to guess x from C, as there is another factor h of h power r. So it's difficult to guess those information, and hence it's not easy to do that, right? So how can a verifier later check if x, if it is the x you are committing to, you use because they are homomorphic. So if there is C1, Gx1, H1, HR1, and C2 is equal to Gx2, HR2. So you have C is equal to C1 plus C2, or G of X1 plus X2 plus H of R1 plus R2. So when you reveal R of X is same as R1 plus R2, comma X1 plus X2. So if you to check the commitments correct, verifier can check if G power X H of R is equal to C, because the whole calculation you don't have to do. You just have to calculate whether G of X of H of R is C, because C is C1 plus C2, which is the value that we are trying to calculate. So network view of a transaction proof is W plus X is equal to Y plus Z. So you have an input, you have a user signature A, you have W is equal to G power W H R1 coins, output is 0, address is C, Y is equal to G power Y H R3 coins. In similar sense, you have these input and output in both cases, input 0 and output 0, input 1 and output 1, where the actual coin values are there, but they are separated by X, Y, Z, Z commitment values, right? So receiver view of the transaction. So you learns own coin value and random number. So again, the input user A signature and W value, Y value, Z value, X value you get. So receiver can check if Z is equal to G cubed H of 1 power 1, 2, 3, 4, 5, then the commitment holds. So that's simple. So, but this commitment commitment to negative values also. If 3 plus 6 is minus 99 plus 108, it hides the negative values. So that's the advantage. But range proofs are required, right? So what are range proofs? I'm not sure how much is sinking into the mind, but I just want to make you aware of what's going on. Now it is up to you whether you want to take this as a challenge and explore some of these that are quite mathematical in nature. Takes some time to understand, but it takes a longer time to code it on some of the Bitcoin scripts that we use. So it may take some time, but yeah, we are supposed to do it. So that's where the zero knowledge proofs and the range proofs are introduced. So sum of inputs should be greater than equal to sum of outputs. Outputs are positive values. So the range proofs are also given here, attached with every confidential transaction. Cryptographic proofs that the transaction is valid, and the signs of bullet proofs very less than 1 KB. So these are Monero's confidential transactions, zero knowledge proofs, and so there is a combination that is going on in Peggy and Victor, and they are trying to check whether how do you know whether you need to do that. So there's a prover on one side, there is a verifier on the other side. There is a non-interactive protocol. So different values are sent. So C is equal to G power X, H power R is Peterson commitment. Then the verifier Victor says, please prove it. Then the challenge is taken and she accepts it, sends a response. The verifier verifies and then you can try to get the value, right? So this is how the non-interactive zero knowledge proofs also goes in and then you can get these values, right? So there are many attacks on the blockchain. Network attacks are also there. Privacy attacks are also there. So each user is identify the address, and you can generate as many addresses as possible. So privacy attacks is as blockchains are replicated at each node. Observer can use the transaction history in the blockchain to find topology of the network and patterns of the transactions, patterns of the users' transactions, and then you can try to look at that, right? Uh, Sometimes user also can be mapped to their geographical location. So if somebody is joining a Bitcoin network, not through a exchange, but actually directly through connecting to the network, downloading a Bitcoin Core software, setting up a Bitcoin Core node, and downloading the entire Bitcoin dataset and being ready. So where you create that account can be giving some information about your geographical location. Like you have geolocation tagging, the IP addresses are belong to a particular uh, geographical location. All Hyderabad addresses or all Bangalore addresses or all Jaipur addresses will be one particular format. So you have these, so you can try to get. So somebody did a experiment and he created this whole map, and he found out that it was 9,354 nodes are there currently in the blockchain, and now they would have grown a little bit, few years. There may be some privacy attacks also. Transaction network can be developed to study the flow of bitcoins. So somebody is sending, somebody is going to somewhere, from there is going to somewhere, from there is going to somewhere. So if you map all these unspent transactions and make a combination of these spent and unspent transactions, then the user network can be developed to study the ownership and spending patterns of the users. We may not know who the user is, but we may know where he's spending the money, what is the spending, where all he can make transactions like that for about a few hundreds of transactions which are in particular geographical location. You can very easily find out. So you will understand all those who have bitcoins how they're spending their money, and that's a privacy issue again, right? So uh, using transaction patterns in the info gathered off the network, adversary can attempt to de-anonymize the user. You can exactly find out who the user is. It's very difficult, but it's not impossible. So you can come to some closer. You can map the Bitcoin addresses with their real-world identities. You can also look at their transaction chats which are going on in Telegram or in WhatsApp or other things. And then if it's a coincidental issue that you both the cases come before you, if you can map both of them, then you can understand that same individual is there. You can map the Bitcoin addresses with their real world identities using us, making it pseudo anonymous. Actually, these are public available vendor addresses. So vendor addresses can be easily found out. And now you look up all the transactions which have those vendor addresses. So you know that all these people are using some kind of material which is available in their address. So you can try to make a correlation, maybe that 50, people you can try to look at it that hand side money should be equal to the right hand side money. So I'm sending to somebody. So I have to use 5 transactions. That is one thing. But sometimes I don't want to use store all these 5 transactions. I want to store one transaction. So I will send these 5 transactions to a blockchain and I get back one transaction as an unspent Download the entire blockchain transactions. You MB maybe 1 TB maybe now. So download the downloadation, and what to do? Analyze all the transactions. Use a classification or use clustering, different mechanisms. Analyze the whole data set. Analyze all the transactions, and you can find out. You can find out how many are according to the P2SH, how many are according to the P2SK, how many are Taproot, how many are Schnorr signatures. Like that, you can very easily. So if you do the analysis of chain hops and how money is being spent and how many money is getting missed out, or people are doing what is called black money. So what you can do, you can analyze the chain hops. So illegal finances, you can understand the identification of flow funds. Every easy alerts about transaction triggers for illicit categories of transaction. Many greater amount has been transmitted. You can find out. Sanction entities, easy tracking source and destination of funds. Suspicious behavior patterns can be generated, and you can very easily get that. You can trace stolen assets, tracing money flow from significant wallets, and checking trace of use of tumblers or mixers, and then you can easily get it. So you can analyze the chain of ownership, revealing any misconduct in activities of previous owner of NFT. So you can provide a verifiable history on of an asset, example, ownership of land of registry. So these things can be easily done. Somebody stealing stolen assets, you can try to find out. Transaction analysis was done on Silk Road also, and Silk Road was a website, something similar to Amazon, but you can see what all can be sold on cryptography, and many of these things are in demand in that this thing. And then, but you sell what is called drugs, marijuana, and pornography content, child abuse, child sex abuse, material, CSAM, all these things, and then it's a risk here. So, but anyway, within a few years, FBI shut it down because it realized that it was a US based this thing, and they shut it down, right? So they also found the arrest of the founder Ross Ulbricht. That is how it does, right? So the Bitfinex hacker also sentenced to 5 years as DOJ ends $10 billion crypto theft cache. So sometimes the thefts are happening from the Bitcoin, right? Somebody is storing a lot of Bitcoins, wants to use it at a later date, but what is actually happening is very difficult. So 95,000 Bitcoin reports were retrieved. That's what you can try to look at it. And then decentralized privacy tool on Ethereum blockchain. You can shuffle user funds, but they were hacker who you misuse that. You lose everything, right? So the transaction analysis already mentioned, transaction output. So one recipient transactions, you change the address. So this address and this address are actually the same. From BitC, again, you get recipient's address, another change address, you get a second recipient address. So each time the different recipients are moved. So all change addresses and original addresses belong to the same addresses. So all change addresses belong to the same addresses. So illegal activities, so digital coins provide anonymity to users, so they can be used for money laundering or illicit activities or irreversible scams like tricking people into sending bitcoins. There is no central agency. You cannot go to somebody and say, "Sir, mere paise dilao." So nobody is going to give you back that money. So there is a central bank digital currency operating on permission blockchain. Is managed by central authorities. It allows real-time monitoring of transactions. So you can't run away with those transactions. All the transactions are mapped on the central bank digital currency. So there is a control privacy for users. So pseudo anonymized transactions for smaller amounts and identity verification for larger amounts are needed. So it's something like bank also. Whenever you make a bigger transaction, there's a phone call which relates where you authorize it, then only it goes. So similarly, you have smaller amounts, you have pseudo anonymized transactions, which are not easy to find out for illegal users, and then for larger amount, you have to physically verify yourself for identity verified. So you know what a lot of money was in the Indo-Pak situation. A lot of money was transferred to bitcoins to the Indian terrorists. So that's a bigger challenge, and then it is difficult to maintain it. Smart contract integration for ensuring payments comply with local laws or internet. So this is the Bitcoin data and the Ethereum data. So where is 24? So the full nodes on Bitcoin use a set of seed nodes to connect to the network. A crawler can be used to find out all the reachable nodes, apply currently online nodes in the Bitcoin network. So you can create another a map like this. This is the map that I talked about, a map of reachable nodes on the Bitcoin network being crawled by Bitcoin node crawler. This is another example that you can look at. So you can do some analysis on blockchain size, how many total size of the blockchain, average transactions per block, total transaction fees, all these analyses. As the blocks are getting added, you can do these analyses. Transaction excluding popular addresses, unique addresses used, mempool close size. So all these things. So there are different Bitcoin projects which are there, Crypto Quant and Glassnode, Merari, YCharts. You can explore different projects there. Yeah, thank you so much. If you have any questions, I'll be very happy to answer.
If anybody is having any doubt, they can put up in chat box.
I will share the material. I can understand your silence. It takes some time for you to understand these things, but the scripts are easy. You can run them on a test network. If that was not discussed, I would suggest that there are test networks for Bitcoin, test network for Ethereum. You can set up the test network and then make these some of these transactions and see and run these transactions and see how they work. So that's one thing, and then so that's the thing that you can look at here. Is there any way? Is there any way that concern can be proxied for miner? Miners proxying themselves is what you're saying? Concern can be proxied. See, miners are competing with one another. So that's how they are. And then if I don't verify other miners' work, when they are unsuccessful, they will not verify mine. So hence a miner is acting both ways. So if he's not able to find at the block, he will verify the others blocks and going. There are selfish miners. There are attacks on that. So that's basically security. Selfish miners are miners who create the block first, but because they got the block first, what do they do? They hide it and they don't add it to the blockchain. They build the second block, third block, fourth block, and so on. And after that, you add all the blocks to the blockchain. Meanwhile, the first block has been added, but by that time, because this fellow is fast, he has got 2-3 blocks we have added. So when he actually publishes all the 4 blocks at the same time, then it's become very difficult. The blockchain is at level 1, but you already reached level 4, or 4 blocks you have reached. And blockchain is at n, but you are n plus 4 blocks. So once you publish all these blocks at the same time, this is at a block n and it is coming to block n plus 1. But by that time, you already got n plus 4 blocks, and all of them are correct. And other miners are verifying it based on what they are starting now. Surprisingly, you see that the blocks are added all by them. So when you study the Bitcoin Explorer, the sequences, every blockchain is not created at 8 to 12 minutes. Some blocks are all created. 4 or 5 blocks are suddenly coming in 1 minute, 2 minute gap. So those are selfish miners' mischief, you can say. So like that, you can look at. I hope I answered your thing. Proxied for miner. Can miners be proxied is what you're asking. I'm thinking like that. So in that case, miners are not proxied because miners are acting independently. In fact, miner pools are acting. It's not a single miner. There will be 10 to 12 people, 20 people working together, putting their resources from different sources, working as a pool of miners, and then that's how it is. So maybe one person is actually managing the whole thing. It's very difficult to proxy a miner. Yeah. Any other questions?
So I think there are no more queries, sir. So we will proceed. On behalf of FDP committee, I would like to thank sir for today's incredible, insightful session on topics blockchain transactions and bitcoins. Sir's clear explanation demystified complex concepts, offering us a understanding of these vital technologies. Thanks once again, sir, for sharing your knowledge and time with us. Thank you, sir.
I'll share the slides with the participants. I'll try to give you the scripts as PPT separately. The remaining text I'll give you as the PDF, right? So the animation part you can download, and in fact I can share the link. Those animations are available. You can go and watch the animation. Thank you so much. Thank you for this opportunity. One advice: please don't get terrified by the by the mathematics or cryptography involved. It takes time. As you are a researcher, most of your faculty members, so please don't lose heart. There are exciting things. So when we cross the bridge, you feel so happy when you get a publication or when you solve a problem or give a solution. Uh, uh, but I can definitely give you one sincere advice is please do something. By staring at the computer screen or listening to so many videos or looking at so many books, nothing will happen. Use your hands-on approach. So please run the codes. Of course, whatever I have shared, I have not run the codes, but my student has done it, and she has executed all that, and she's the one who is publishing the papers. I only look at how the code is running and what are the difficulties in the code and explain. So please code. So when you see that scripting can be done, when you see that smart contracts can be created, please create. Please run the codes. Please use your hands-on approach and try to do that. Wish you all the best. Thank you so much.
Thank you, sir. There will be break till 1:50. Till then, you can go for lunch, and we will meet again at 1:50.